What we're going to do now is take a look at antiderivatives, or finding an integral. So before we said, okay, we've got a function f of x equals x squared, and we can find its derivative, which is 2x. What we're going to do now is say, okay, we have a function 2x, and we want to know what function or functions has 2x as its derivative. So symbolically we're finding the integral of 2x dx. So we're finding it like we differentiated with respect to x. Here we're finding the integral with respect to x. Right, so what function or functions has 2x as a derivative? And just knowing what we know right here, we could say, well, x squared has a derivative of 2x. But what we're going to do here is always add a constant c. And why do we do that? Well, I know there's a lot of functions that have 2x as a derivative. X squared plus 7 has 2x as a derivative. X squared minus 3 has a derivative of 2x. X squared plus 1. These all have a derivative of 2x. And why we add this constant is because we can find the derivative of this, and then if we add on a constant, the derivative of this is always 0. So for all of these different functions, where the only difference is their constant term, they still all have the same derivative. Okay? So that's all we're doing when we're finding antiderivatives. We're just going backwards. Take a function, we can find its derivative. Now what we're going to do is take a derivative and find the function that it's associated with. Okay, so we knew that if I had the function 7x plus 2, or some linear function, we always knew that the derivative is going to be the slope. We know when we had a constant term, the derivative is always 0, etc. So now what we're going to do is attempt to find derivatives, find antiderivatives for various functions. So for example, if I had an antiderivative of 7, I want to know what functions have a derivative of 7. And we know that 7x would have a derivative of 7. But then again, we're going to add the constant c to say, well, there are a bunch of lines that have a derivative of 7, a bunch of lines that have a slope of 7. The only thing that's different about them is their y-intercept. So that's how we can get that antiderivative. So what we're going to do is, let's take a particular situation. So we know that, let's say, velocity function negative 32t plus 32. That's an example. So we know the velocity function. What we want to do is find the actual position function. So what we're going to do, basically what we're saying is, okay, what's the position function that has this as its derivative? So what we're going to do is find integrate, find the antiderivative of this. Okay, so using our rules, we can say that, well, this is just some of these derivatives. We can pull constants out in front. And what we have, we'll get negative 32 t squared over 2 plus 32 t plus, again, some constant. Okay, and what we, simplifying a little bit, we've got negative 16t squared plus 32t plus some constant. Right. And if we check this, you can always check your work. If you take the derivative of this function that you found, you should get, if this is a position function, we should get, as a result, the derivative, the velocity function we have. So the derivative here would be negative 32t plus 32. Okay. The only thing we need to find is this constant term. And how we'll find that is by using what are called initial conditions, or given some point, we can solve for our constant c. So let's do that. We've got our function here. We want to figure out the constant using initial conditions. Now let's suppose we know that position, so we have a position function So here's our position function. We know position when t equals 2 is 5, or we know that so 2 equals 5. What we can do is solve for our constant term. So we know this equals 5. So this gives us negative 64 plus c equals 5. Well, there c equals 5. So this gives us our actual position function, taking into consideration those initial conditions. Try another one. So we want to take the antiderivative of 3x plus 2 dx. So finding that antiderivative, we can, using our rules, so we know we can break these up. And then we know that constants come out in front. And so the antiderivative of this would be 3/2 x squared plus 2x plus our constant. And again, to check our work, we can find this derivative. 2 times 3/2 is 3 times x plus 2. Okay, so this matches with what we're trying to find. So given this function, let's say we know that when x equals 2, the function is equal to 8. So when x is 2, the function value is 8. We just use this information to solve for our constant c. So 8 equals 3/2 x squared plus 2 times x plus a constant. So this is 8 equals 6 plus 4 plus c, which gives us c equal -2. So our function, specific function, ends up being 3/2 x squared plus 2x minus 2. And in fact, the derivative of this is going to be 3x plus 2. We just now know the specific constant to go along with it.